In this problem, one end of a uniform beam weighing 52.7 Newton and 3.12 meter long is attached to a wall with a hinge as shown in that figure. The other end is supported by a wire making equal angles of 27 degree with the beam as shown over here and with the wall as shown over here. In the first part, we are required to find out the value of the tension in the wire. In the second part, we need to compute the horizontal and vertical forces on the hinge. Now, let's move towards the solution of that problem. First of all, we will make a free body diagram showing all the forces acting on this uniform being weighing 52.7 Newton and having length of 3.12 meter. These are the four forces which would act on this uniform beam of weight 52.7 Newton. Now let's name these forces shown in that figure. The first force is this tension force, which is being acting on that end of the uniform beam due to this string. This force is due to the weight of our beam, which is equal to 52.7 newtons. This force is the vertical force or the vertical component of the force on the hinge. Let's denote that by FV. This is the horizontal component of the force. Let's denote that force by FH. As we know that, according to the conditions of equilibrium, all of our these forces are laid in XY plane. So we would have three conditions for equilibrium. According to the first condition of equilibrium, our sigma tau z should be equal to 0. Also, we know that the torque is equal to R times F sine of theta, or we can write that equation as R and multiplied by the perpendicular component of the force, which is F perpendicular. Here R is the position vector. Now, in order to find out the value of sigma tau z around a particular point, we have two assumptions or two conventions. The first convention is we choose that point to be our axis of rotation from at which maximum number of forces act, and in this case that point is the hinge of that uniform beam over here shown by the orange color. The second assumption is that the torque produced by a force is called to be positive if that force tries to rotate the object in the counterclockwise direction, as does this tension force. Now, according to this convention, if a force tries to rotate an object under consideration in the clockwise direction, then that component of torque would be considered as negative, which in that particular case would be this weight force. Now, in order to use this first condition of equilibrium, which is sigma tau z equal to 0, I need sum of the angles over here to resolve my forces into their perpendicular components. So let me first draw a perpendicular over here to calculate different angles involved in that particular case. I have drawn a perpendicular line to that end of my uniform beam which is being attached by a string. Now, if my this string is making an angle of 27 degree with this horizontal wall, then the angle made by the string over there or that vertical wall or line would be equal to 27 degree. Now, if I draw a horizontal line over here, then this complete angle would be 90 degree. So if I want to find out the angle which that uniform beam would make with that horizontal line, then my angle would be equal to 90 degree minus 27 degree minus 27 degree, and that angle would be this one over here, and that angle is equal to 36 degrees. Now if I consider this right angle triangle formed by this horizontal, this vertical portion of the wall and this uniform beam, then the angles in the right angle triangle is equal to 180 degree. So if the total angles of the right angle triangle are equal to 180 degree, then if that angle is 90 degree and this angle we have just found to be equal to 36 degree, then this remaining angle over here would be equal to 180 minus 90 minus 36 degrees, and that would be equal to 54 degrees. Now if that angle is equal to 54 degrees over here, then that angle would also be equal to 54 degrees. Now let's apply the torque equation over here. The torque due to these two forces would be equal to 0 because R in that case is equal to 0. Now consider this weighting force. If we consider the length of that rod to be equal to L, then that weight is being applied at the middle of that rod which is equal to L by 2. So for that case, our R would be equal to L by 2. Now there is one force which is being acting at that point, and that is the weight of that uniform beam, and it is equal to 52.7 newtons. Now one thing here is very important, which is the sign of that torque. Under the action of that force over that object which is beam in that case would try to move in the clockwise direction. So the torque due to that component of force would be negative. So I have put the negative sign over here. Now in that case, the torque is acting vertically downward, and I need the component of the force which is perpendicular to that R, which in that case is equal to L by 2. So I have to resolve my weight into its perpendicular components and radial components. The perpendicular component of the weight would point in that direction. Now if I apply the rules of trigonometry, then that component would be equal to W sine of 54 degrees. Now there is another force which is being acting on over that uniform beam of weight 52.7 newtons, and that force is the tension force over here. And if we consider the length of that rod to be equal to L, then that force is acting at a point which is L from that origin. Now, here the sign of the torque would be positive because this tension force is trying to rotate the object in the counterclockwise direction as shown by the arrow over here. Now, in that case, the torque is acting in that direction and I need the component of torque which is perpendicular to this R or L according to this relation of torque. So my component of this tension force which would be perpendicular to this R would be something like that, and let's denote that with T perpendicular. Now, what would be the magnitude of this TL? According to the trigonometric identity, if my this tension force is making the angle of 27 degree with this beam, then this TL would be equal to T times sine of 27 degrees. And according to the condition of equilibrium, that thing should be equal to 0. Now, if I want to find out the value of this tension force from that relation, then this can be found as T, and that thing would be equal to W by 2 sine of 54 degrees divided by sine of 27 degree. Now over this weight is equal to 52.7 Newton as given in the statement of that problem. Now upon substituting the value of this weight over here, the final value of the tension would be T, and that is this weight 52.7 divided by 2 into sine of 54 and sine of 27 degrees, and our final answer would be equal to 47 Newton. This was the first part of the problem in which we have found out the value of the tension in the wire and its value is equal to the 47 Newton. Now in the second part we have to find out the values of the horizontal and vertical components of the force on the hinge at that point. So we have another condition of equilibrium which was sigma fx, and that thing should be equal to 0, which is the summation of all the forces in the x direction should be equal to 0. Now over here we have this tension force which is not pointing in the x or y direction. So we have to resolve that tension force into its horizontal and vertical components which are here x and y components. So the vertical component of this tension force would point in the upward direction as shown by the arrow over here. Let's call that Ty. There would be a horizontal component of that tension force which points in the negative x direction, and let's call that Tx. Now in order to calculate the value of this Tx and Ty, we have to use the trigonometric identities. then Tx is equal to T cos of theta and Ty would be equal to T sine of theta. Here is a tricky thing, which is the angle theta. Now, this tension force is making the angle theta with this horizontal over here. So, theta would be equal to this 36-degree angle plus this 27-degree angle over there. And this would be equal to 27 plus 36, and the answer would be 63 degrees. Now, upon substituting the value of tension and angle theta in these two relations, the value of Tx would be 47 times cos of 63 degree, and the value of Ty would be 47 into sine of 63 degree. On solving that relation, my answers would be for Tx is equal to 21.33 Newton, and for Ty my answer would be 41.87 Newton. Now, according to our conditions of equilibrium over here, which is sigma Fx equal to 0, or the summation of all the forces in the x direction should be equal to 0, there are two forces which are acting in the x direction. One is the horizontal component of the force which is acting in the positive x direction. So I would write it as F of h. Similarly, there is the tension force which is acting in the negative x direction, and that component of the tension is Tx. So I would write minus Tx, as that component is acting in the negative x direction. And this thing would be equal to 0 according to this condition. Now, for finding out the value of this Fh would be equal to Tx. Now, the value of this Tx has been found over here, and that thing is equal to 21.33 Newton. Now, we have the third condition of equilibrium, which was sigma Fy should also be equal to 0 if we want our body to be in complete equilibrium. So, there are three forces which are acting in the y direction. The first force is this vertical force which is acting in the positive y direction. So, I would write it as plus Fv. There is this weight which is acting in the downward direction. So, I would write minus sign with this weight. There is also a component of this tension force which is acting in the positive direction. So, I have to write plus with this component of the tension which is acting in the positive direction. Now, according to this condition, I have to write 0 over here. Now, from that equation, we have to find out the value of this Fv. So, Fv would be equal to W minus Ty. Upon substituting the value of this weight, which was given in the statement of the problem, and it is equal to 52.7 newtons, minus this Ty, which is equal to 41.87, over vertical force on the hinge would be equal to 10.8 newtons. So, we have found out the value of the horizontal and vertical components of the forces on the hinge as asked in the second part of our question. In the next problem, there are three particles which are attached to a rod at different positions. The position of the first rod is given over here and its mass is 52 gram. Similarly, the position of the second particle is at 45 centimeter and the position of the third particle is 65 centimeter from the origin. You have to find out the value of the rotational inertia of this complete assembly, and if the rod was pivoted in about the center of mass of the assembly, then you have to find out the rotational inertia of that rod about the center of the mass of the assembly. Let me make a diagram of that particular case. We have a rod in an XY plane. Let's say it lies on the x-axis for the sake of simplicity, and there are three particles attached to that rod. The first particle has mass m1, the second particle has mass m2, and the third particle has mass m3. m1, m2, and m3. The distance of the first particle from the origin is r1, the second particle is r2, and the third particle is r3. And if these three particles are lying on x-axis, then we can say that that thing is x1, that is x2, and the third one is x3. In the first part, we are given that our this rod is pivoted about the origin. So in the first part, we have to find the rotational inertia of the assembly around this axis or around that point. So the rotational inertia relationship is would be equal to m1 r1 square plus m2 r2 square plus m3 r3 square. We are given with the values of this m1 and the distance of this particle from the origin. So for the first particle, the mass is 52 gram, and that thing would be equal to 0.052 kilogram times its position from the origin, and that thing is equal to 0.27 meter square. Similarly, for the second term or the second particle, the mass is given to us to be 35 gram. So in kilogram, that thing would be equal to 0.035 kilogram, and its distance from the origin is 45 centimeters. So in meters, that thing would be equal to 0.45. Similarly, for the third term, the mass is given to us and that thing is 24 gram. So in kilogram, that thing would be equal to 0.024 kilogram, and when multiplied by its R, so that thing would be equal to 0.65 meters. The final answer of the rotational inertia of that assembly around that point would be 0.021 kilogram into meter square. So now in the second part, I have to find out the rotational inertia about the center of the mass of the assembly. So first I have to find out the position where my center of mass would lie by using the relationship for calculating the position of the center of mass. So let me copy that thing to the other slide. According to the parallel axis theorem, we know that the rotational inertia about any arbitrary axis is equal to the rotational inertia through the center of mass plus mass times h square. Now in the second part, we have to find out the value of this ICM. So the ICM would be equal to I minus mh square. We have find out the value of this rotational inertia about that arbitrary axis to be I. We know the mass, total mass of this assembly, which would be equal to m1 plus m2 plus m3, but the only term here which we don't know is this h, which is the distance between the two axes. First one, which is this, the axis which lie at the origin, and the second axis which would lie at the center of the mass. Now in order to find out the value of the center of mass, we can see that over all the three masses, or this rod lies on the x-axis, so the position of the center of mass can be found out by this relation of xcm, and that thing would be equal to m1 x1 plus m2 x2 plus m3 x3 and divided by m1 plus m2 plus m3. We know the value of this first mass, which is 52 gram, and its position from the origin, which in that case is 27 centimeters. Similarly, for the second object having mass m2, which is 35 gram, and its position from the origin is 45 centimeter. Similarly, for the third particle, the mass of the third particle is 24 gram and its position is 65 centimeter from the origin. Now if I would substitute these values, the position of center of mass would come out to be 0.41 centimeter. Now if I want to find out the value of the rotational inertia through that axis, or the axis which pass through the center of mass, and I know the value of the rotational inertia through an arbitrary axis, then on using this relation, the value of the ICM would be this I, which I have found in the previous part, and whose value is 0.021 kilogram, minus the total mass of this assembly, which is equal to 0.111 kilogram, times the distance between these two axes, and which we have calculated by this xcm, and that thing is equal to 0.41. So on taking the square of that term, the value of the ICM would come out to be 2.34 cross 10 raised to power minus 3 kilogram into meter square. In this problem, we are required to find the average angular velocity of a diver who makes 4 complete revolutions on its way from a 40-meter platform to the water below. Now to find the average angular velocity for this dive, we need to find the value of time in which he dives from 40-meter platform to the water level below. This can be found by using the following formula. As we know that the formula for vertical displacement is given by y is equal to y naught plus v naught yt minus 1 by 2 gt square. Now if a diver makes a jump from a platform which is 40 meter above from the water level, then we can say that initially its position is 40 meters above the water level, and this water level is at 0 meter. Alternatively, we can say that a diver makes a jump from initial position, which is given by y naught is equal to 0, to a point which is 40 meters below that point. So y, or final position, would become equal to y is equal to minus 40 meters. These are the two ways of seeing that problem. Now we can use either these values in this relation to find the value of time, or we can use these values in that relation to find the value of time. The only thing matter is how you see this problem. Now if I use these values in that problem to solve for time, I can say that y is equal to minus 40, y naught is 0. We are given with 0 initial vertical velocity, so that y naught would also be equal to 0. I know the value of g, which is equal to 9.8 and t square. Now if we rearrange this equation to solve for the value of time, we would be obtaining that relation. T is equal to 40 cross 2. This minus sign would be cancelled out by that minus sign, and this whole relation is divided by 9.8. As it is t square, we need to take the under root to cancel out the square on t. If we solve for time, we would get a value of 2.86 seconds. Now this is a time in which the diver makes 4 revolutions. Now we are required to find the value of average angular velocity, which can be calculated by using the following formula. Average angular velocity is equal to delta phi by delta t. Phi is given by 4 revolutions. The time is calculated by using these calculations, and it is equal to 2.86 seconds. If we solve this equation, we would get the answer of 1.398 revolutions per second. If we want to find the answer in radians per second, we know that 1 revolution is equal to 2 pi radians. So if we multiply this relation by 2 pi radians, then we get the answer in radians per second instead of revolutions per second. So 2 pi radians is equal to 1 revolution, and my final answer would be 8.8 radians per second, and that is the answer which you are required to fill in the evaluation or assessment form. Now the next problem is in which an astronaut is being tested in a centrifuge. Human centrifuges are exceptionally large centrifuges that test the reactions and tolerance of pilots and astronauts to acceleration above those experienced in the Earth's gravity. The centrifuge has a radius of 10.4 meters and in the starting rotates according to that relation. When time t is equal to 5.60 seconds, we are required to find the angular speed, tangential acceleration, and the radial acceleration of the astronauts. We are given with the value of angular displacement, which is given by the relation as phi is equal to 0.326 radians per second squares into t square. Now if we want to find the value of angular velocity, we need to take the derivative of angular displacement. So angular velocity is the time derivative of angular displacement. Now if I plug in the value of angular displacement in this relation and take the derivative, then I would get the value of angular velocity. So if I plug in the value of this phi, I would get d by dt 0.326 radians per second square into time square. Now this value is a constant. We will take the derivative of this t square, which would be equal to 2t, and if I multiply by this 2 by that relation, I would get 2 into 0.326 radians per second square into t. If I multiply 2 by this relation, I would get 0.652 radians per second square into t. Now this is the relation for angular velocity. If I want to find the relation for angular acceleration, then I need to take the derivative again of this angular velocity to convert this relation into angular acceleration. So if I take the derivative, alpha is equal to d omega by dt. The value of omega is 0.652 radians per second square into t. Now this value is a constant, and if I take the derivative of t, it would be equal to 1. So the value of angular acceleration would be equal to 0.652 radians per second square. Now in the first part of this problem, we are required to find the value of angular speed at time t is equal to 5.70 seconds. We plug in the value of time in the relation of omega, which we find to be 0.652 into t. The time is given by 5.60 seconds. If I plug in the value of time, I would get 5.70 seconds is equal to 3.65 radians per second. In the second part, we are required to find the tangential speed. The formula of tangential speed is calculated in the previous section and is given by the following relation: Vt is equal to omega r. The value of omega is calculated in the first part, and we are given with the value of radius to be 10.4 meters. Now if I plug in the value of omega and this radius, then I would get the value of tangential speed. Omega is equal to 3.65. The value of radius is 10.4 and the answer would be 37.97 meter per second square. In the third part, we are required to find the value of tangential acceleration. We have derived a formula to calculate the value of tangential acceleration to be alpha r. We are given with the value of alpha to be 0.652 radians per second square and the value of r is 10.4 meters. If we solve that relation, we would get the answer of 6.78 meters per second square. In the last part, we are required to find the value of radial acceleration. We have the formula for radial acceleration, which is AR is equal to omega square r. The value of omega is found in the first part and it is equal to 3.65 radians per second. 3.65 square multiplied by 10.4, and after solving I get the answer of 139 meters per second square, and this is our final answer for radial acceleration.